So, if we are squaring the r plus dr whole square, so we have a r square plus 2r dr plus dr whole square. So, we are discussing about the elemental strip of the drawing process, in which different stresses are acting along the x axis, and whatever be the conical shape is there, for that we have taken the forces along the x axis. Now, we have to take the radial in radial direction. For that we have to go for the our screen. So, in screen you are observing that we have a pressure here on this direction, and for that we have analyzed the forces along the x direction. For that we had a expression. So, we will see that one. In another regard, we have to see the another side view, or you can say from the front, if it is the front, whatever the side is there, or along the force direction, drawing force direction, and here we have taken the elemental strip in this figure 2. And figure 2 we have to discuss. So, now for the x direction, after neglecting the higher term, we have r d sigma x plus 2 here in bracket sigma x would be there, plus p is there, 1 plus mu by tan alpha. Into dr. This must be equal to 0 for the equilibrium. Here sigma n and p are related to our yield criteria, and the del r which we have taken here, now we are considering the another element, means from the force direction, if we have the segment like this. So, this is the segment from here to here, and the distance between this one is we have taken as a del r, and the forces that are acting here, the stresses which are acting here in this direction, that is a sigma theta. And here the small angle that we are considering is d theta. So, we have a strip here. From the top, already I have told you, or we have gone through that, the forces acting here is p cos alpha minus mu p sin alpha, and here from the inside there is a sigma r is there, and this one is a center line. So, now consider the forces, then we can write that minus p cos alpha minus mu p sin alpha, this one is taken as a negative one, into r plus del r. R plus del r and d theta into dx, this is the total area and the force that is acting on this element, minus whatever the sigma r is there into the radius in d theta into dx. Now, the another component, that is minus 2 sigma theta sine of d theta by 2 into the del r into the dx, this is equal to 0. Again, if we neglect the higher term and keeping alpha as a small, the equation will become, this will give us that p 1 minus mu sin alpha plus sigma r, or here this must be multiplied by r d theta dx. And this would be equal to 0. Here we have neglected the higher term because the alpha is small, or we can say that sigma r, this one is nothing but equal to minus p 1 minus mu sin alpha this is equal to minus p, near about the pressure whatever we have applied, because this term is near about 1. Since the circumferential strain rate is same as the radial strain, so according to our von Mises stress strain rate law, so now we are applying von Mises stress strain rate law. So, this one provide us the sigma r, this must be equal to our sigma theta. From here we can say that we have a principal stresses the principal stresses are sigma 1 is equal to sigma x and sigma 2 is equal to sigma r in radial direction is equal to sigma theta also is equal to sigma 3, means we have a sigma 1, we have a sigma 2, we have a sigma 3, and finally this value is nothing but is equal to minus whatever the force we are applying. So, if we put in the von Mises, means sigma 1 minus sigma 2 whole square, sigma 2 minus sigma 3 whole square, plus sigma 3 minus sigma 1 whole square is equal to twice k square or sigma y. So, this will give us sigma x plus p, this is become equal to our yield stress, or here we can say that the value of a p, the value of a p would be equal to our sigma y minus sigma x. Now, this one has to be substitute in whatever we have done for the stresses in x direction. So, if we put the value of a p in a equation that we have derived earlier, that r dx d sigma x plus 2 into sigma x plus p into 1 plus mu by tan alpha into dr, this is equal to 0. We have r d sigma x plus 2 into sigma x plus sigma y minus sigma x into the phi. We are taking one constant, that phi into dr, this is equal to 0, and this value of a phi, you can say that where phi is nothing but here we have taken as 1 plus mu by tan alpha. So, in this way we have a value of a phi, and if we rearrange it, in such a way that it will become dr by r means here we have a dr is there, we have a plus sign is there. So, we are keeping both the side, right hand side as well as left hand side, one element would be here. So, dr by r, this will be become minus negative time of d sigma x upon 2, again the phi term is there, sigma y plus 1 minus phi into sigma x. So, this is our term. Now, we have to integrate both the side. Here we are integrating left hand side as well as the right hand side. So, finally, we have log of r, this would be equal to, this will become plus 1 upon 2 phi minus 1. Then again we have a log of total whatever be the values are there, means phi sigma y plus, means here it would, we can write as a 1 minus phi or phi minus 1, phi minus 1 into the sigma x. Certainly a integrating factor would be there, constant would be there, let this one is a c. Here we have to put the value that at r, that at r means diameter initial, half of the diameter initial, the sigma x is equal to the back stress whatever we have applied, that is a force divided by the area. So, I am writing it here that when we can say that at r is equal to d initial by 2 this sigma x stress, that would be equal to whatever the back force is applied divided by the area initial, or you can say that the value of a c, this will become log of di by 2 minus 1 upon 2